Hello everyone. So this is our midterm project in AI and cybersecurity, and it is about cloud-based P malware detection API. So it is portable execution malware detection. We do classification on whether a given executable is malware or not. So this is my project report, and here what we discuss is about our dataset, which was Ember 2018 V2 dataset. It contained around 1 million data points, out of which 800,000 were training data points and 200,000 were testing. Out of 800,000 data points in training, 200,000 were somewhat not usable because the level was not that we required. So out of 600 data points, we trained our model. So let's talk about what is PE files. So PE is portable executable file that is used by Windows operating system, and they have a structured layout. So they have headers, they have characteristics, architect, entry point, section layout, and so many things. And this can help us understand whether a file or an AX executable is malware, is a good file for our system or not. And let's talk about this. Is one of the picture that I got from the internet, and it says that it's a 32-bit P file structure. So there are many data that you can see in the pictures, many headers. So yeah, and let's go to malconv. So talking about our architecture, malconv is a deep learning model designed to detect malicious Windows portable executable PE files, and it is based on CNN. And we analyze raw byte level content of PE files here. So we extract the data. Our binary files has byte level data, so we extract that data and try to have some meaningful insight from that. And so this is the architecture of our Markov. So first one is the raw byte. So this is the input layer where we get our data, our binary files. So we put into embedding layer. Embedding layer is something that we have seen similar to our ngram, I would say. So whatever the data we have from have we get, we just make into one hot encoding, something kind of like that. And after that we pass to 1D convolution layer. After that there is a multiplication and sigma layer, and we do a max pooling. So max pooling is done because it's not just looking for a small set of location, it's looking at a larger set of location, and we can get maybe not different distant values as well from max pooling. And a connected layer and a layer linear, and the last is softmax layer because it's a binary classification. So yeah, and yeah, we have used Pytorch for this. So Pytorch is an open source machine learning library primarily developed by Facebook, and we used Pytorch API to make our model, and we trained our data in made from Pytorch model. And you can see Pytorch mainly work on tensors. So there is data source, tensors. We use GPU for this that was provided by Google Colab, and multiprocessing data is done best tensor loop. And now going to AWS SageMaker. So deployment was done in AWS SageMaker. It's a fully managed machine learning service provided by Amazon Web Services. It simplifies the process of building, training, and deploying. And you can see here is ECS, Amazon SageMaker, and S3. So we can use containers, like we can use a container system. So we just make a Docker file and containerize our system and put that in AWS SageMaker so that our model can be deployed. And here is notebook instance, so we can write code here as well. So we can use AWS provided container as well from here, model and containers. So, and talking about our project, it was divided into three parts: building and training the model, deploying the model as a cloud API, and creating a client application. So it was building was done by Python 3.10. I guess I used 3.10, but it depends upon many system I use. So in Colab it was 3.10. In my local system it was 3.8. I guess not in my local system, in my AWS EC2 instance. So I tried a various resources to see where I can get more benefits out of it. So yeah, and we use Pytorch 2.x, Ember dataset here, and deploying the model. So yeah, we utilize AWS Academy Learner Labs, and we made sure that we don't go beyond our quota to spend all our $100 on here. And client application was deployed using streamlit web application. Streamlit is a library that's easy to use and creating a web interface. So yeah, project methodology. So building and training the model. Uh, so yeah, sampling of the dataset was done because yeah, it's a very large file and we don't have enough RAM in free Google Colab. So sampling maybe on 100,000 data sets, data points or 200,000 data points based on the and deleting the variables as you go on training. That also helps to make sure the notebook doesn't crash. And training process, yeah, min max scalar was used to featurize and numerous data, so it could be fed into neural network to get better results. Okay, deploying the model, yeah. Okay, yeah, the resources shared in task description were very helpful and guided in the process. So yeah, it was very helpful to go through the resources that was provided. And yeah, project results, deploy evaluation, yeah, so we can see the training and validation loss plot, history plot. So you can see the loss decreased from 0.67 to 0.29 training and 0.64 to 0.29. I also utilize early stopping so that it doesn't overfit the model. So yeah, I think that helps. And we can see our result and conclusion. We achieved 82% accuracy and 0.78% precision and 0.877% recall. As I remember, we can see later on we have around 0.82 F1 score, and this is our confusion matrix. You can see here the false positive is too high, and that's not a very good thing. But since we had limited resources and not much time, so we could not use more training. Conclusion. So yeah, what were the some of the things that I got stuck on? So we could have used an advanced deep learning architecture, but we couldn't due to the time limitations, high-end resources. We utilize only free Google Colab accounts. So yeah, transfer learning was not done. We used scratched. We trained our model from scratch. And yeah, the dataset were diverse enough already. And there are some of the resources that I used to complete this project. Now let's go to different part. So here is my GitHub account, and this is the report that I just showed you. This PE file is the file that can be used to uh, provide a API while using Docker. So yeah, it takes input as a file and it outputs if the file is um, but malign or benign. So yeah, and this is my training notebook. Also, this in a while, and this is our min max scalar that I've used in Xtrain. And this is the overview. You can go through this, how to do all of those. And nearby should be my notebook. So notebook is here itself, I guess. Yeah, here is my notebook, and you can see I did not download all this data because the storage was also issued in Google Colab. So I had already mounted all the data in my drive. So I imported the drive, and this is not required. And yeah, we have to install Ember and leave. So I didn't read this. I had already read those all, and I created a pickle file because this step also takes a lot of time, and we have to do a lot of time running this code blocks. So yeah, so I created a pickle file for both train test, having this preprocessed, this step preprocessed, so we don't get stuck in the same. We don't waste our time. Yeah. So yeah, we can load this pickle file if you want, but later on you'll see that you won't require that as well. And this is the code for sampling. And I have sampled on a white train. So I have taken 60,000 samples from each classes and created sample X train and sample Y train. And this also I have pickled. So I have taken 60,000 and 100,000. So I have created different data sets according to that. And I've copied in my drive. So yeah, now you see that I have um, read 100,000 sample points for X train and Y train. And this is our model. You can see we have input length of 3 million, embedding of 8, and window size of 5. So stride is 5 minus 3, 2. Two neural network, one embedding layer, one segment layer, next pool layer, two linear neural network, and one segment layer. That is the output for our binary classification. This is forward pull, and this is our model. So you can see our model architecture here clearly. So now I used min max scaler, and that the feature range is from 0 to 1000, and I fitted that, and I transform my X train. I have not loaded my X test till now because of the RAM constraints. I will load that later and transform that later. So yeah, and so it would be min max scalar. So yeah, I have also put this scalar in a dump file, in a pickle file, so that I can load when in deployment or later on. So I don't have to do this step again. I've copied that in my drive. This is, you can see the my directory structure. After a while, you can see some pickle finds, some checkpoints, some pickle file for data and all. So our training set has 200,000 data points and 2,381 features right now. So this is again, we had train and test, but we require validation for early stopping and for not overfitting the data. So we create that, and we also make tensors for that, and we make a batch size of 4,000. And we delete our variables as we go on, so that we don't want our notebook to crash. So this is helpful when you don't have enough RAM. Now we're checking if CUDA is available. If not, CPU can be used. And we have Atom optimizer there. Number of epochs I've used 10 here. And you can see early stopping, the code for early stopping. The patience is 5. And this is the code we have lost here. Epoch loss, validation, and early stopping is here. And we train our model. And we can see the training and validation loss. So it seems good. And we have now loaded our data after we have deleted all our variables that we don't require. And we also have sampled our X test and Y test because it's too large, 200,000 data points. So yeah, and still we just test for 1,000 data points, and we transform from, because the this test data set is not scaled, so we scale from min max scalar. And now we evaluate our test, and we can find the test accuracy of 82, precision of 78, recall of 87. Now we plot our confusion matrix, and we save our best model to, we save our weights, and we save our checkpoint, and we put that into drive. And what you can see, we also did a sanity test on loading our model once again, and yeah, it did work. What you can see is the model was developed using Pytorch and trained over 200,000 data points with the help of Google Colab provided T-Food CPU. The training and testing accuracy are pretty good. F1 score. So 2 times precision times accuracy divided by accuracy plus precision equals to 0.828. So around 83%. There seems to be a higher false positive, and that is somewhat concerning. More training data should be used to make sure that doesn't happen, and more higher end resources would be required to develop and train more complex and powerful models. So this is the thing that we saw from our model. And right now, if we can see, so I've started working on deploying the project, but it's still taking some time to do that. Just a minute. So I think it's, for now, this would be it. That it was a fun project. I like working on it. The time, okay, the thing that was challenging in this project, where it was the code or the data set and the libraries all were outdated, so we have to take care of that. That was the challenging part, but as this is our job description when we go in the real world, so yeah, it gave us a sense of time, it gave us sense of more research, it gave us a point of this real world architecture and mm, resources that we utilize in AWS, GPUs, and also, yeah, in a whole, this was a very good learning curve during our midterm project. I learned very much, and I think this has made some changes in me to view about the midterm project, about any project that has time constraints. So yeah, thank you, everyone. I hope you have a good day.